So as we dive into lipids, there are classifications. There are the isoprenoids, which are the steroids and lipid vitamins. There are the terpenes in plants that also fit into this category of isoprenoids. The more talked about group of lipids are the fatty acids, and we will momentarily be diving into the structure of the fatty acids. We will begin with the simple fatty acids and build from there. We will be talking about the triacylglycerols as a storage form of fatty acids, because in actuality, fatty acids themselves, they have a carboxyl polar head group and a long hydrocarbon side chain. They act like detergents. So a free fatty acid in the body, and some of you who study exercise phys know this, a free fatty acid in the body is very deleterious, very damaging. So in order to store them, they're stored as triacylglycerols, where there's that glycerol backbone is esterified to 3 long hydrocarbon side chains. Now, the next class will be the glycerol phospholipids. This primarily comprises the group that we know as the quote-unquote phospholipids, but there is one sphingolipid that has a phosphate group that would cause it to also be classified into the group that we are informally know as the phospholipids. So I'm just going to make note of that if you take the one group from the sphingolipids plus the glycerol phospholipids, this is the quote-unquote phospholipids. We talked briefly about the waxes and the very important signaling role of eicosanoids, so we'll jump into each one of those, but let's begin by just simply looking at the structure of a simple fatty acid, which is not so simple because that long hydrocarbon side chain can vary quite a lot. Now let's begin by looking at the carboxyl group of a fatty acid, and I want you to recognize that it is ionized, meaning that it has lost its acidic proton. Now this is going to make a ton of sense when I remind you that the pKa value of this carboxyl group is somewhere between 4.5 and 5. So when we think about that and we recall that the physiological pH of a cell is around 7.3 or 7.4, we recognize that this particular group, the pH, we have passed the pKa value. So the species that predominates at physiological pH will be the ionized species. That is, the predominant species will be the one that has lost its acidic proton. So when we look at that and frame it within the larger molecule itself, what we recognize is that it makes it so that the molecule has 2 regions. It actually literally has a polar head group and a long fatty acyl side chain, right? A long hydrophobic hydrocarbon side chain. Now, if you look at that, it's going to remind you of something that we recently have covered, and that is a detergent, right? It's got the polar head group and the long hydrophobic tail. So you might be thinking, wow, detergents, aren't detergents kind of bad for membranes? And you got it. If there's a lot of free fatty acids, sometimes we call them FFAs, free fatty acids. If there's a lot of those floating around within the cell, they can literally act as detergents, solubilizing membranes and literally wreaking havoc within a cell. Therefore, the concentration of free fatty acids is generally kept at a minimum to try to stop these deleterious effects. And we'll see in fact that structurally most fatty acids are stored at any given time as a larger molecule, a triacylglycerol, and that's what we know as storage and dietary fats. So let's take a moment to deconstruct the overall structure of a fatty acid, beginning first with the long hydrocarbon side chain. And I have a feeling this is going to be a super fun part because you'll recognize the hydrocarbon tail as something that nutritional facts tell us a lot about. For example, you may have looked at the label of some sort of food and noticed that it either does or doesn't contain saturated fats. What that refers to is the state of the hydrocarbon tail. So not only does the hydrocarbon tail vary in length, but it also varies depending upon the degree of unsaturation. So a saturated fat, meaning that all of the carbons are bound to hydrogens and there are no double bonds in the chain, versus an unsaturated fat where we see maybe more than one or more double bond that characterizes that side chain. And in a moment here, we'll look at a fat that is not saturated. So the picture that we're showing here, which actually is of laurate, the fatty acid named laurate, is actually a saturated hydrocarbon tail. It has no double bonds in that tail. Now, if we want to look further at the overarching structure of this fatty acid, we can cut it off at the next level up, which would be at the carbon of the acyl group here. And so that leaves us with what we term fittingly the fatty acyl side chain. So remember, we've talked so much about what an acyl group is. So essentially that idea of this being a C double bond O bond R, and that's what we're referring to when we look at this fatty acyl side chain. So essentially in a fatty acid, it means everything but the negatively charged or ionized oxygen. So the fatty acyl side chain is just the C double bond O bond R. We can then further speak about the whole fatty acid in its entirety as being that entire molecule that we see there, ranging from 12 to 20 carbons and almost always even in number. So when we talk about the whole fatty acid, that's when we're speaking about the numbers being even, and we tend to see those being more common, and that's literally because fats are generally synthesized 2 carbons at a time. We remember, maybe many of you remember, that it's synthesized from the precursor metabolite acetyl-CoA. So that makes sense that it would be built 2 carbons at a time, and we would see those being the most common. And in fact, if we look down below, you'll notice that some of the most common of the fatty acids are oleate, which has 18, palmitate, which has 16, stearate at 18, which stearate literally means from steers. It's a fat that comes from steers, palmitate from palm oil. So these are some of our most common fatty acids, and you might be noticing that palmitate and stearate, these are saturated fats, but now I want to turn our attention to a mono unsaturated fat, oleate. So notice that oleate is abbreviated as 18:1, and in a minute we'll talk about exactly what that means. But oleate is a mono unsaturated fatty acid, meaning that it has a double bond in its hydrocarbon tail, whereas palmitate and stearate do not have a double bond, and that's why they're abbreviated as 16:0 or 18:0, meaning they have 18 carbons in their chain, but none of them are double. There's 0 double bonds in that side chain. Now, before we leave this behind, I want to make sure to make reference to nomenclature and how we either number or name the carbons in a fatty acid. So we may either start with carbon 1, the carbonyl carbon of that carboxyl group, numbering down 1, 2, 3, 4, and so on down, or we may use a more common nomenclature where the first carbon attached to the carbonyl carbon is called the alpha carbon, and then alpha, beta, gamma, delta, epsilon, and so on down. But where things get a little bit confusing is with the terminal carbon. Always, always, always in a fatty acid, the last carbon is called the omega carbon. It doesn't matter whether it's stearate with 18 carbons or whether it's palmitate with 16 carbons. That final carbon in the chain is still called the omega carbon. And that's going to play a huge role in the nomenclature that we use for all of our fatty acids. So without further ado, let's take a moment to look at the difference between a saturated fat and a saturated fatty acid and an unsaturated fatty acid. Let's start with a monounsaturated fatty acid and then move our way into a polyunsaturated fatty acid that might have more than one double bond in the hydrocarbon side chain. Here we have a famous monounsaturated fatty acid called oleate or oleic acid, and you'll notice that it does indeed have one double bond in its hydrocarbon side chain. Now let's number and find out between which 2 carbons it takes place. So carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So between carbons 9 and 10, 11, 12, 13, 14, 15, 16, 17, and 18. So this is an 18 carbon long fatty acid with a double bond between carbons 9 and 10. So we have a shorthand notation that we use for that. We say that this is an 18 carbon long fatty acid with 1 double bond, so 18:1, and then we say delta and 9 because the double bond occurs between carbon 9 and 10. So you notice that a kink is definitely built into oleate. Now, if we also take a look, though, at PUFAs, or polyunsaturated fatty acids, we're going to see even more kinks built into their hydrocarbon side chain. One of the most famous fatty acids and one of two that are essential in your diet, yes, fats are essential in your diet, linoleic and linolenate are the two essential fatty acids, also known as linoleic acid and linoleic acid. You'll notice here that there are 2 degrees of unsaturation. So once again, if we count through the carbons, 1, 2, 3, 4, 5, 6, 7, 8, and once again, double bond between carbons 9 and 10, 11, 12, 13, 14, 15, 16, 17, and 18. Aha, another 18 carbon long. So we'll go ahead and write down that we have an 18, but this time colon 2 because there's 2 double bonds, delta 9, but also 12. So delta 9, 12. Now, this is a very famous fatty acid, but you probably never heard it referred to as 18:2 delta 912. However, you have heard of this based upon its omega carbons. So when we refer to an unsaturated fatty acid based on the omega carbon, we count backwards from the terminal carbon. So we would go backwards from 17, 16, 15, 14, 13. And so it's 1, 2, 3, 4, 5, 6 carbons back, and we call this an omega-6 fatty acid. So you most likely have heard of an omega-6 fatty acid. I bet you've definitely heard of an omega-3 fatty acid, and sometimes they're even also called N-6 or N-3. So let's actually draw what I would say is the most famous fatty acid, the omega-3 or the linoleic acid, so linolenate or linoleic acid, or the omega-3 fatty acid that's essential in your diet. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yet again, there's a double bond between carbons 9 and 10, and then yet again, a double bond between carbons 12 and 13. But then 14, 15, there's another double bond between carbons 15 and 16. So let me just make sure we denote that accurately. So here comes another double bond, adding yet another kink into this chain. And there you have it, the 18th carbon. Let's make that red. So carbon 18, and counting backwards from there, we'll find that this is indeed an omega-3. So the 15th carbon, 18 minus 3 is 15. And so we'll denote this as the ever famous omega-3 linoleic acid, also sometimes known as N-3, but also, of course, we can use that same notation of 18:3 delta 9, 12, 15. That's another way we could think about referring to this. Now, when we consider all of these fatty acids, you know and love linoleic and linoleic acid because they are polyunsaturated fatty acids that are found in foods associated with health. For example, avocados, olive oil, flaxseed oil, walnuts, that you can get these amazing fatty acids, not to mention fish. And so, of course, that'll excite CJ. And so we'll recognize that there's something special about them with regards to their health-giving capacity. Now, part of that has to do with the way in which they pack. So if we think about our saturated versus our unsaturated fatty acids, and I'm going to draw this in sort of a cartoon style. We know our saturated fatty acids have a polar head group and long hydrocarbon side chains that have no kinks in them. Now, when these pack next to one another, say within a membrane, they are very close enough that an induced dipole interaction, we know as fondly as London dispersion forces, can begin to be a very strong force in holding these together. So if we consider the ways in which the length of the hydrocarbon side chain affects that, we would recognize that the longer the saturated hydrocarbon side chain, the more room for London dispersion forces to form. So therefore, the greater the melting temperature. So the TM, or melting temperature, of this right-hand side, these very highly saturated but also long fatty acyl side chains, will have a higher TM than the shorter one. So the longer the hydrocarbon side chain, the higher the TM. You know, butter is solid in your refrigerator, a saturated fatty acid, whereas your olive oil tends to stay much more liquid. So let's think about that phenomenon. If we now think about the idea that in our polyunsaturated fatty acids, we start to see these really big kinks built in, and, you know, give the artistic interpretation there. And so these big kinks in these fatty acids prevent them from engaging in close packing. So the more degrees of unsaturation, the more distance tends to occur, the more fluidity tends to occur, the less London dispersion forces. So up here, the longer the hydrocarbon side chain, the higher the TM, because there are more London dispersion forces. So the longer the hydrocarbon side chain, the greater the London dispersion forces, and the higher the TM. So on the other hand, the more degrees of unsaturation, the less London dispersion forces, and the lower the TM. So polyunsaturated fatty acids have a much lower melting temperature. They tend to be liquid at room temperature and even refrigerator temperature, and those tend to be those that are associated with health. More on that, I promise, to come.